Ladies and gentlemen, hello and welcome back once again. It is 4 o'clock Eastern on a Tuesday, which of course means it's 1 o'clock Pacific, where I am at the moment in a hallway in a hotel downtown San Francisco at the Kafka Summit. But that means it's time for the briefing room. Yes, indeed. My name is Eric Cavanaugh. I will be your host, even traveling on the road here at the Kafka Summit. Really cool stuff going on. Wow, let's dive right in. So the topic today, contain yourself. Development just got easier. We're going to talk with Des Blanchfield, Dr. Robin Bloor, and of course our good friend Alvin Richards from Aerospike. Really cool stuff. There is a spot about yours truly. Enough about me. Hit me up on Twitter at Eric_Cavanaugh. The mission of the briefing room, of course, is to reveal the essential characteristics of enterprise software. We do that by hosting live analyst briefings. You folks out there in the real world can help us by asking good questions. So please don't be shy. Send your questions in at any time during this event. We'll queue them up at the end. We got a lot of content today, so I'm going to move quickly. April is database month, analytic platforms. That's what we're talking about. And things are changing, folks. The speed of business is changing. Really, and it's kind of apropos, I suppose, that I'm at the Kafka Summit here. Apache Kafka, of course, is all about streaming analytics, but streaming data in general, kind of replacing that middleware part of the stack, at least for future-oriented companies. But the database is what we'll talk about today, and containers, and how do containers change the nature of application development? Well, it turns out Des loves containers. Yes, Des Blanchfield, our data scientist, has a fetish for containers. It's true. So Aerospike is the company today. It's a NoSQL high-performance, flash-optimized database. Speed at scale is what they talk about, folks. So if you're one of these new data-driven businesses and you're not talking to Aerospike, you should be. There's Alvin Richards calling in from a remote location on the other side of the United States in New York, VP of Product at Aerospike. He's a smart guy, so ask him the hard questions. Don't let him off easy, folks. There's Dr. Robin Bloor. He is our analyst of the day, du jour, so to speak, but he is joined by the inimitable data scientist, Des Blanchfield, one of the top 10 LinkedIn profiles down on the night. Crikey. With that, I'm going to hand it over to Crikey himself, Des Blanchfield, to take it away. Flying containers. All right, buddy, the floor is all yours.
Thank you, Eric, and thanks everyone for joining us today. So yes, I do have a fetish for shipping containers, which we won't go into today. I'm going to fly through the front end of my slides very, very quickly because I just want to set this scene for kind of what the concept of the container means to computing systems and software and development environments in general, and then get to kind of how we got to where we are now and where we're going to and why it's so important. So containers, in the context of shipping containers, just to set the scene, up till about 1956, shipping was an interesting challenge. Anything that moved around the planet was essentially put into a wooden box or wrapped up in nets and tied up and strapped to the deck of a boat, and we prayed and hoped it got to the other end, and invariably it was damaged in the process and everything was stacked on top of each other. It was a very risky, dangerous, expensive thing to do. But as late as 1956, a gentleman by the name of Malcolm McLean transformed that whole world, particularly of shipping and logistics, by introducing a thing in the form of a standard box, a standard metal tin box to load all this material into of any form and create what we refer to as a bimodal container. That is, it's something that can go on multiple types of transport. So in this case, it can go on trains, it can go on trucks, and it can go on ships. And they came in a couple of standard formats. In fact, there were 3 of them that were more well known. There's a 10-foot version, a 20-foot version, and a 40-foot version. And if anyone's played with Lego, you can get the concept that these fit nicely into different combinations of, 4 10-foot versions fit into a 40-foot version, and you can stack them very nice and squarely and cleanly. And in fact, we do. There's an image of a bunch of them being rack, pack, and stack, and you can see they fit very, very cleanly together. They are a very efficient and compact use of space. But the key thing is that you can put whatever you like inside them within reason, and as long as it doesn't move around too much, you can safely transport them around, and whether they sit on the back of a train, on the back of a truck, or loaded on the deck of a boat, it's completely transformed the way things are moved around the planet and logistics and shipping. And in fact, here's a thing called the Triple E from the Maersk line. This is a real boat. It holds 18,000 shipping containers and safely moves them around the planet with whatever you decide to load in them. And to put this in context of how great this is, the very first ship was a refitted naval boat, and it carried something like 56 containers, and everyone thought that was an amazing thing. But now we've got people producing boats that carry 18,000 of these standardized containers. Just as a bit of a side giggle though, no matter how great standards are, and they are a wonderful thing, sometimes unfortunately not everyone gets the memo, and you might have great containers and great standards, but somebody will push the envelope and not read the manual. And this apparently is a fairly common occurrence in certainly certain island areas where these big boats can't get in there. And I'm sure that's a fairly precarious way to move your container around. So I like to introduce very quickly with these shipping containers, because the ISO shipping standard container is a standard shipping container is a perfect analogy for the modern application container. More lately, we've seen a group called HashiCorp introduced a product called Docker, and I use the shipping container because they use exactly the same analogy to describe the way their applications are packaged and bundled with their logo, which is a little whale presenting to be a ship, and it's got little shipping containers on the back of it. And there are a number of options on these. There's Kubernetes, there's different operating systems like CoreOS that provides capability to do it, but Docker is probably the one that's got the majority of the mind share in the place at the moment, and it's relevant to today's topic. So containers are not a new concept, though. We've been doing these things for a long time in various formats, but what's new is the scale and speed at which we're using them. And I'll get to that very point leading up to my very last slide, and you'll understand what I mean by that in just a few minutes. So as I said, they're not a new concept, but CPU technology just wasn't ready in the way it is today, and you'll see why. So we were containerizing things as early as mainframes, and we containerized whole operating systems in part. We call them LPARs. And in VMS and Solaris, we effectively had this concept of containers that we try to contain an operating system and a virtual machine. We've had programming languages like Java where we have these virtual machines, and we call them Java VMs, and we packaged up apps in the form of essentially a compressed file. At operating system level, we've had BSD with Jails, user mode Linux, OpenVZ, where we try to take an entire machine and put it into a virtual machine. But what we're really trying to do is take something that was originally hardware and run it into a virtual machine, and what's referred to generally as a P2V experience, physical to virtual. So run lots of virtual machines in one physical dedicated machine. The reality was that virtualization on 16 and 32-bit CPUs was very hard, and most of the virtualization was done in software. We weren't able to do it inside the chip in a hardware sense. And at the time, we were still really dealing with the transition in kernel development from what was then symmetric multiprocessing style to large-scale compute to what has now essentially been containerization. Also, semiconductor development hadn't really reached the boom that was driven by mobile devices, and particularly mobile phones. But of interest, just in the context of 32-bit CPUs, there's an image there just briefly. That's a picture from Minecraft, and that's a 32-bit CPU emulator built in Minecraft, the game, and my 11-year-old son plays with it and does calculations with it. So you can imagine the difference in power we now have in computers in 64-bit architectures is so great that we're now playing with games and building blocks, and those blocks are being used to build 32-bit CPU emulators. But the technology has now finally caught up, and we've moved from virtual machines to containers, and this is a significant transformation in how our app stacks are built and deployed and implemented. 64-bit CPUs with virtualization physically built in the core at semiconductor level have come about. Virtualization's moved from a software issue to a hardware issue. We no longer have to write all the virtualization in the hypervisor in software. We can do it in hardware built into the core of the chip. And we've seen the reign of what I refer to as PC servers, and this is the x86 family that have in the Intel world VTX, and in the AMD world AMD V built into the chip itself. We also made the realization that to go big, we effectively had to go small. That is, we had to get down to the nitty-gritty of the detail of how we were building apps and how we were containerizing and deploying them. We've experienced platform as a service come about, and there are some famous brands like Heroku and EngineYard that provided us an entire platform stack as a service. And we then only had to worry about writing a code and packaging it, shipping to them. And that changed the way we approach development as well, because we can now just bundle our code, put it into effectively what we consider a container, and run it. Things got really interesting, though, when a gentleman by the name of Randy Bias, an associate of mine that I met recently in Sydney when he was here with his wife, he quoted a gentleman by the name of Bill Baker from Microsoft, and he used this term cattle versus pets. And there's a slide that he put, I think it was 2012, the first saw the light of day, where he referenced Bill Baker, who I think was a distinguished engineer at Microsoft at the time, who created the term, but I think Randy Bias was the first to put it into a slide. And he talked about the transition from scaling up in a vertical sense where virtual environments and virtual servers were treated like pets, and you gave them a name and you cared for them and you loved them and you looked after them. If they got sick, you nursed them back to health. And the transition to what we call scale out, where virtual servers and eventually containerization were just given numbers, and you treated them like cattle. So we made this transition from treating our infrastructure and apps and containerized software as pets to treating them as cattle and just getting to the point where if something got sick, we just killed it and moved on. And so what that did was it put us in a situation now where development now isn't a case of building an entire app and putting it into a dedicated virtual machine on a hypervised environment. We just build apps and put them into these tiny little things called containers. We can deploy them very rapidly, and they're the minimal amount of business logic and technology wrapped around the software is necessary just to instantiate them. And you'll see the context of this very, very soon when we go through the presentation that we're about to see. So to encapsulate all of that, what we've discovered is that the effective leveraging of the modern container frameworks is giving those people who adopt them a real competitive advantage, and we're about to see that in real detail. And with that, I'm going to hand over to Alvin to show us exactly how they've, Alvin Richards from Aerospike, to show us exactly how they've gone about leveraging that model and framework for a competitive advantage. Alvin, over to you.
Perfect. Thanks, Des. Let me go and share my desktop. Okay. As you can see, I have the world's messiest desktop. Okay. So we're going to talk about how development just got easier, really. Yeah. So I'll start with the conclusion, which is containers plus databases mean you can end up with some happy developers, but ephemeral containers and database gives a set of DevOps headaches. And, you know, what I'm going to talk a little about is the ease of development, but a lot about how to ease some of those DevOps headaches. Really, the 4 things you need to consider if you're thinking about putting a database in a container is what you do about redundancy, the forming of the cluster, how it self-heals as containers come and go, and how does your application find this ever-changing and morphing beast. So that's the conclusion. So hopefully by the end, in the next 30 minutes, I'd have answered some, if not all, of those questions. So I'm a lover of old black and white movies, and, you know, Laura and Hardy had some great quotes, and yes, we have got ourselves into a fine mess. If you think about how you're building applications at the moment, you're ending up with some database, perhaps a relational database at the bottom. You've got a caching layer in front of that, and you've got many tiers of applications trying to access that data in different ways. And you've probably got some data lake on the left-hand side. And you're trying to kind of act as a system integrator to put all these things together. So our architectures look a bit kind of wonky and complex. How we actually deploy that software, again, is a mishmash of technologies. Whether you're using Chef or Puppet or Ansible, your developer has got the basic problem of how do they get their version control software out through all of these environments, and their production environment ends up looking like their development environment with the same set of dependencies, so that you have, as a developer, some chance of actually debugging problems seen in production. And finally, you've got a set of infrastructure where you don't really fully utilize them. A traditional database on the left-hand side sits on top of an OS file system, a page cache, a block interface before it gets to the actual physical device. What you really need is, for example, in database land, you want your database to talk directly to the memory system and then directly to the devices so you can actually fully utilize the capacity and capability of not only kind of SSDs and flash, but any new future developments like transactional memory. So let's try and meet some of those challenges. If we think about containers, they're there for encapsulation, deployment, and isolation. The databases has got to now do the persistent scalability and all of those other attributes in order to create a scalable persistence tier. Okay, so we talked a little bit about, Des talked a little bit about containers. And the whole premise is that you build, ship, and run, and the things that you build with are ultimately the images that you run with. I kind of think of them as containers giving you these key characteristics, which is they encapsulate all of your external dependencies, whether they are your operating system version or patches or particular packages you need to install, but they also encapsulate your code as well. At runtime, they give you process isolation, so they give you this kind of nice kind of, quote, virtualized environment to run in, so you're not getting processes interfere with each other. And, you know, one way to think about this is faster, lightweight virtualization. That's not actually true, but it's a good way of thinking of it. I'll go through this example really quickly, but here's an example of a Docker file, and you can actually see it's relatively easy to understand what you're specifying in terms of what your image should be. You're specifying, in this example, I'm using a particular version of Python, I'm adding code from a local directory, I'm doing some Linux package updates, and I'm installing some Python dependencies. And so it's very easy to see the encapsulation of everything that my image that I'm going to run is. And once I've built that image, I can now deploy that and run it on my desktop, and I can run it in my production environment, and it's the same image with the same dependencies. You're not asking your sysadmin to go and install a bunch of packages inside a virtual machine or your bare metal box. There's a big open initiative to ensure that container standards are interoperable, and you can see every man and woman and child and their dog is on this list. I'm sure that list is much longer, but you can go to opencontainers.org to see all of the organizations that are contributing to that standard. Okay, so now we get to a busy picture. In the world of Docker, there are many components with strange names. So in the top left, we've got a container. We've talked about containers. That's how you encapsulate your code and your dependencies. Those containers are essentially an image, and the image is run by Docker Engine, which is the big whale in the middle. And as you can see, the big whale in the middle is running lots of containers, so you can have many images all running at the same time. Now, there's a couple of other ancillary technologies, and we'll walk through these in the demo. But you've got, once you have got an application, it may be composed of multiple containers. So Docker Compose, which is the squid or the octopus on the bottom right, I guess it's an octopus, isn't it? That is essentially there to orchestrate all of these different containers. How do you get the Docker engines in the first place? Well, it's Docker machine. That will go provision you one of these runtime environments on your own bare metal or in your own data center or even on the cloud. And eventually, when you want to have some high availability solution and you want to spread your load across multiple Docker engines, top right is where Docker Swarm comes in, and then that's essentially there to cluster lots of engines together. So it's a very busy side, but we'll talk through all these in detail with some examples. So how does Aerospike fit into this? Well, the bottom line is we are designed to do high-performance database processing. We are a key value store, and typically we can condense big farms of NoSQL solutions and get a better density of 10 to 20x. And we simply do that because we have a proprietary log structured file system that allows us to avoid all the file system and page cache inefficiency and go directly to those block devices. So we're kind of designed from the bottom up to utilize the characteristics of Flash. We combine this with a hashing and partitioning algorithm so we can distribute data across tens of, or hundreds of nodes. Essentially, our primary index is red-black, that's the key part of it, and then the data is held on SSDs across that cluster. What it allows us to do is dynamically add and remove nodes, auto-rebalance the data across those nodes, and auto-heal if there's any failure of those nodes. And we'll see how some of those characteristics work really well when you are dealing with ephemeral containers. As I said, it's optimized for throughput and latency. As you can see, there's a whole bunch of charts here. that allow, that show that we can get 10 to 20x throughput in comparison to other NoSQL solutions. And there's plenty more information up on the website if you want to dive down into the details. A couple of use cases. Real-time fraud prevention is one of the kind of mission-critical use cases where Aerospike is used. If you think about what happens when you swipe your credit card, there are enormous amounts of rules that need to be processed to understand whether that transaction can be approved or not. And as fraud gets more sophisticated, the number of rules that you need to look at and process are changing by an order of magnitude. And so this is where Aerospike fits into some very well-known credit card processing companies. How fast can it go? Well, if 1 million writes a second per node isn't fast enough for you, then we know we've got your back. As you can say, we can scale up to 50, 100 nodes, and so therefore you're going to get that scaling in a linear fashion. All right, where else can Aerospike be used? Well, it's also, you can think of it as a cache with persistence. And so again, we can do a server consolidation by getting more out of your compute than other solutions in the space. All right, that's the sales and the marketing slides over with. Let's talk about Aerospike and Docker. We talked about the kind of key aspects of data redundancy, self-healing, discovery, and your application discovery in the database tier. So how does Aerospike does this? Well, we've got inbuilt replication. That means that you can specify your replication factor, and that means that you can store n number of copies, 2, 3, 4, 5, 7, depending on whatever you need. Aerospike's architecture is shared nothing, which means that there are no particular nodes with a specific role. So as one node disappears, it means that the other surviving nodes can take over the responsibility of the data and the replication. That all happens automatically. Clearly, as you lose nodes, you'll then need to make additional copies of the data. This is a self-healing part to ensure that you're meeting those needs for replication and availability. And finally, we have our clients for all the popular languages. You can see some of them listed there. But essentially, those clients automate the discovery of the cluster. So the cluster topology is changing. There's no need to restart your clients. They're automatically discovering what that topology looks like. And so this takes away a great burden from not only the operational side of keeping the cluster running, but also from the application side, because you don't need to build in reams and reams of specific logic to deal with many failure cases. It's all being handled for you. All right, that's the kind of theory. What I want to do is spend the rest of the time kind of taking you through a little demo. Now, this is a live demo, and the chances of everything working are obviously slim because it's a live demo, but you'll see what's happening. You'll probably see me making many typing mistakes too, which is always fun. So what we're going to do, we're going to try and build an application. We're going to start off with development. We're going to do the development on our laptop. Then we are going to push that application into our production environment, which is going to have a HA proxy for load balancing, and then we want to scale our database service. And what we'll see is you don't have to write any specific code in order to make this happen automatically. So here's our application. It's a small web application, and Aerospike is the database behind. And what we're going to get through this demo is to our production environment, where not only we can scale the web tier automatically, we can also scale the database persistence tier. Okay, so let's go build an application, because that would be the fun part. Let's start off with, here's our piece of Python code. And this is all fairly standard. I'll point out a couple of things as we go through. So what we can see here in line 41 is in my Flask code, what I'm doing is establishing a connection to the database cluster. And so what we need is a node or a set of nodes, because as soon as we contact the first node, the algorithms will automatically detect all the other members. We've got a simple application which is going to take in a request, and then what we're going to do is we are going to do a series of operations. We're going to apply those, do some increments, and then we're going to create a response form, and so that we'll see the application running. So that's the code. This is all posted to a GitHub repo. There's links included to that, so you can go and play with this yourself. So let's actually start using Docker Compose, which is going to orchestrate our two containers. One container is our web application. The second container is our database. So if we do Docker Compose up, what this is going to do is orchestrate the starting of our two containers. As you can see, the logs are printed to the output here, and you can see those containers running. So if I walk over to my web browser, if I refresh this page, we can now see that we've got a simple voting application, Coke, Pepsi, or tap water. So we can pick any of these particular selections. And as you can see, what we're doing is that web application is interacting with the database to store the results of what I've currently voted for and various other things. So very simple application. How did we go about orchestrating that? So let's go back to our editor. So we saw this Docker file earlier, and this Docker file is describing the image for our web application. So as we said earlier, it's describing that we want to use Python and we want to use a specific version, in this case 2.7. We're going to install a number of packages, Python deb, libSSL. These could be any packages you want to. We're going to then run any dependent, we're going to add any dependent modules that this application needs. And then finally, we're going to run Python with our application. And so this then constructs the image that we then execute in a container. How did I compose these services together? So here is our compose file. So this is fairly simple. What we do is we describe two services, web and Aerospike. So web has got a couple of commands. First is build. This will tell Docker to automatically build the image if I hadn't already built it. It's going to tell me what ports to expose. It's going to tell me I'm going to link to this other service called Aerospike, and we'll talk about that in a second. I set a host name and some environment variables. So my second service is Aerospike, and I'm going to use an image. And so I'm going to use an image that is hosted on Docker's hub service. I could host it locally, but I'm going to use Aerospike, and I'm going to use a particular image called Aerospike server. And I'm specifying here the label, which is the latest, i.e. give me the most up-to-date version of Aerospike. And that's all I've had to do to compose this service. All I then did was Docker Compose up with this YAML file, and now Docker has started, Docker Compose has started these two containers. And so we can simply see how quickly it is to containerize your application and start running your application. Okay, so let's go on, and this is, the slides just talk through these particular details, so we just talk through that. Okay, so part two. I built my application. It's awesome. I think you've all seen the application. I think you all agree it's awesome, and it is going to be fundamentally change how we think about web applications and doing voting. And now we want to roll that in production, and quite realistically, we think one web server and one database is not going to be enough. So what I want to do is I want to put a load balancer in front of the web traffic so that I can run the application code behind the HA proxy, and then I can scale the web tier as I get all this incoming traffic to vote for Pepsi or Coke or tap water. Now, in a previous version of the demo, I had candidates for the up-and-coming election in the States, but I figured I'd make it a bit more politically correct for this demo. All right, so what we now need to talk about is Docker networking. So if we go back to our previous image, do we want to run all of these processes on a single server? Well, I think the simple answer is almost certainly not in production. And so what we now want to do is we want to run these services across many hosts. So this gets us onto Docker networking. And this kind of fairly complex diagram shows the fact that we have multiple servers. Each one of those servers may need to connect to different, each one of those containers may need to connect to different containers. So we want to ensure that our HA proxy containers can talk to our Aerospike containers and so on and so forth. What Docker is allowing us to do is to create virtual networks between these Docker engines or Docker hosts. And so this means that you can, just in the way that you'd have created a VLAN to encapsulate or to localize the traffic between your web application and your database, in Docker you can actually do the same thing to ensure that only the right containers can talk to each other over essentially a virtualized private network. And so what we'll do is we'll set this up to show that we can actually spread our application and ensure it remains connected correctly, but also connected privately. So let's go and scale our web tier. All right, so here I am in my production environment. I can now do Docker compose up and do -d this time just to run this in the background. And as you can see, we've got our HA proxy, we've got our application, and we have got our database up and running. So if I go back to my application over here, you can see in the bottom part of the screen, I've actually got a visualization of the cluster so you can see what's going on. So currently, we've got 3 hosts in this cluster. We've got our HA proxy, which is this green square box over here, and we've got our database on the environment. So we're running the same bits under the same Linux version, same dependency, same packages. And so this gives the developer the first win. They can now really execute and debug and run their application just as it would run in production. So we wanted to scale the web tier. So we can really do that very simply now. We could do Docker compose, we can scale, and we want to use a service name of 5. So what Docker compose is now doing is it's ensuring that there are at least 5 containers running in this cluster of that service. So if we go back to our visualization, we'll see we've got lots of containers now running the same image. And due to the magic of HA proxy, my application is still running. And as you can see, the IP address that's being recorded is different. So let's go and we can go and have a quick look in the database. So I can do a Docker run -it-rm. I'll need to say I'm on the prod network because this is now a private network. And I want to run Aerospike tools, and AQL is just the command line tool for Docker, and I need to give it a host name. And this is where what have I typed in incorrectly? Docker. And I look blankly at myself going, that should be correct. All right, so in all these cases, it's always nice to actually have here we go. Oh, that's the wrong one. Sorry about that.
It's a double hyphen on net.
Ah, there you go. Thank you.
That's all right.
All right. you know, you look at things several times. You go, I know there's a mistake there somewhere. All right, so that's going to log into the Aerospike shell, and we can go and actually look at the contents of the database. So as that's doing that, let's go and look to see how we did this. So here is my compose file for production. I've got a number of services, HA Proxy, Web, and Discovery. We can now use some of the extensions that Compose lets you to do. So Compose gives you the ability to compose from existing compositions. So what I'm doing here is HA Proxy is going to extend an existing file called HA Proxy, and then we're going to inject some additional information about a particular environment. Now, we'll come on to what these constraints will do in a second when we come to look at our database node. So we've got our HA Proxy, we've got our web, and instead of building an image, I'm now using a particular image that's going to download from Docker Hub, so that's great. And let's go down to Aerospike. So here's our fourth service. Again, it's going to extend from a base YAML image, and so this is a great way for the ops side of the house to inject some standard behavior over and above what the developer needs. So what I'm going to do here is I'm going to, in addition to that, I'm going to specify a particular label. I'm going to say this is my prod cluster. And the key additional thing I can do with Docker Compose and Swarm is I can specify affinity rules. So it's clear with our database that we don't want to put all the containers that are running our database cluster on the same host. So what I'm doing in this affinity rule is ensuring that when that container starts, it can't start if there is already a container with this same label already present. So this ensures that we only have one container running Aerospike per host. And so the rules that you can specify are quite powerful and to ensure that you can actually meet those development characteristics. So if we go back into our shell, here we go. So let's start from test.summary. So I'm running Aerospike's command line tool in a Docker container as well. So you can all right. It's my day for demos not working as I'd expect. Okay. All right. Here we go. There you go. So here is our summary. As you can see, we've got votes coming in. We've got the total number of votes, 15. And as you can see, we've recorded in our statistics the votes from each one of those IP addresses from each one of the web servers. So you can see this is a very simple use of the database, but this is also showing that we're actually load balancing across all of those web servers in order to spread the load, and we're just recording the fact of which ones we use to record the vote. So let's go to the final piece. Again, this is just explaining all of those rules. The final piece is to now scale the database tier. Now, if you've seen so far, we haven't had to change our application code or even the application that was running in order to scale the web tier. We just added more application servers, and behind HA Proxy, we could now spread the load. Didn't have to change anything, didn't have to restart anything. It'd be great if the database had exactly the same characteristics. So let's go and do that. So back on my command line, I can say Docker Compose scale Aerospike equals 3. So it's going to now start 2 additional Aerospike containers. And if we go back to our visualization, we can now see that there are 3 database containers now running, and our application will carry on working. And so the combination of Docker and Aerospike with the integration that we've done means that from a developer perspective, you get a very easy way to build database applications, and for your ops team, a very easy way to scale out the database tier without having manual procedures to do reconfiguration of either the database or the application. we're taking advantage of Docker's underlying containerization and networking. So let me quickly go back and give you a little insight about how we did that. And let me do this quickly so I can wrap up. So internally within Docker, there is an event API, and that means that you can inspect events of containers starting and stopping. And so what we've utilized is a framework called Interlock, written by our good friend Evan Hazlitt, who provides a framework that you can create plugins so that you can see these events and then respond to them. So Aerospike's Interlock plugin essentially automates all of the cluster management so that these clusters will automatically reform as containers start and stop. And this kind of really alleviates the burden of using this type of topology in production. There's a quick example of what that plugin would look like and getting the event and then doing something with it. Again, there's all of this is on GitHub, so you can look at the code afterwards. Finally, considerations. So where should you store your data? Should you store your data inside the container? Well, if containers are ephemeral, when the container goes, so does your data. So typically, your choices are out on the right-hand side. Either you store the container externally, as the data for the container externally to the container on the host itself, or you store it in some kind of network storage, for example, in EBS. And the advantage of the deployment on the right is that you've got a separation of concerns, and you can utilize all of your favorite tools, for example, EBS snapshotting, in order to do backups. The diagram on the left is great for developers in pre-production or test environments, because essentially you may want to throw the data away after the test is finished. So you've got this flexibility in deployment styles, but you should really think about what this means for your particular application and what are the consequences of losing that container. There is a new form of data containers which have been introduced relatively recently. We're still running performance tests and reliability tests to understand whether that is a great way to deploy a database. So here's a quick summary. One solution from dev into production, and running Docker and databases in production is advantageous because the ops team gets to specify the versions that should be used and the various policies, but it gives the developers a very easy way to go build images that are now in conformance to the needs of the ops side. So this is a great way to marry these two things together and get a very simple and flexible way to go build database scale-out applications.
All right, with that, I'm going to hand it back over to, actually, I'll take it for one quick second. I'll hand it over to Dr. Robin Bloor. Let's move these slides forward a little bit. Actually, hold on. We'll get some good questions here in a minute, too, folks. Don't be shy. You can ask questions at any time. We'll queue them up. We'll have a couple minutes, but I have to say, that was some pretty cool stuff, and I got to hand it to Des Blanchfield for doing some real-time troubleshooting of real-time app development in a real-time briefing room. That was pretty cool. Oops, I gave it to Alvin by accident. Hold on, Robin. I'm handing you the keys now. Take it away.
Okay, thanks for that, Eric. Yes, Mr. Blanchfield. He's not an Australian. He's a parser. I'm going to tear through this because Des has said half of it already, and I'm actually really interested to kind of discuss what we just saw in the demo and the kind of implications of it within the Aerospike environment. So yes, we got containers. The issue is that the IT industry continually reinvents the wheel because the IT industry continually reinvents the computer. So, you know, you get new operating environments arising, and we do the same things to them to make them work. They start primitive, they get better, they become defunct because hardware eventually makes them obsolete, or something else comes along and attracts our attention. So the roughly repeated melody is what kind of happened with the mainframe. It happened in different ways later, but you know, Single stream of work was a series of jobs. Then you got time slicing. Then you got resource management within a partition. Kix was kind of like that in its early days. Sophisticated scheduling leading to software stacks suddenly becomes possible, and then multiple apps within stacks. And you just get more and more sophisticated as time goes by and as any environment gets more and more, more and more code gets written. This is, I thought this was worth throwing up. It's Docker versus the virtual machine. And really all that this diagram is telling you is that virtual machines are horrible in terms of their resource squandering. But they were invented, in the days, around 2000, 2002, people were running Windows servers that were using 2% of the resources. That's absurd. You even had Sun servers that were only using 6% of the resources. Crazy things were going on because in one way or another the software had not kept pace with the iron in terms of its usage. And Microsoft hadn't helped because it wanted its application, it wanted one application per Windows instance, so it could charge you per instance. And when Linux came in, Linux was also like that in the sense that people were just, it had a really neat small footprint. You could take an old PC and run it as a server in the data center, and that kind of stuff was going on for a long time. And then, the VMware got more and more sophisticated, but you still got this horrible wastage of resource with the different guest OSs sitting over a hypervisor, which is run by a host OS, The situation on the right is Docker. I'm not going to go through it because whatever needs to be said about it is going to be said by smarter people than me a little later. But the point about Docker is you can, roughly speaking, it's 4+ more applications per server, and that's simply because you are saving an awful lot of resource in various ways, and that's with no performance degradation. Resource efficiency, this is just my list of things that I used to think about in the old days when I had an honest job and actually used to write code. In order to make an environment efficient, eliminate unused executables, share all resources without causing queuing, release resources when no longer needed, share common data, use reentrant code. And that's this is the kind of series of things that happen when you go from a trivially single stream environment like Hadoop was in its when it was born. And you start adding stuff, and it became as no surprise to me when Docker emerged, because there was obviously a crying need for it because there was so much resource wastage going on. It would be perfect if we could do the whole containerization this time in a way that's hardware independent, because that, in the end, what actually tends to sabotage all these ideas is that hardware moves in a way to make the old software architecture somehow redundant. So that's really all I've got to say. There are a number of questions I have, but to be honest, I think my main question for Alvin really is, I'm well aware that Aerospike is an incredibly efficient environment, and if you want to run extremely high transaction loads, then it's buttoned down the use of resources in a way that very few database other products do. So my main question is, I can see what Docker gives you. You kind of demonstrated that. What do you actually sacrifice? Is it slightly inefficient than just writing native code sitting over Aerospike? What do you lose?
That's a great question, Robin. It comes down to, the tests that we do in our lab before we validate solutions, we want to ensure that we understand what the degradation is. And, typically it's going to depend on your hardware you've got, but it's somewhere between, 5 and 10% typically. I'd encourage everybody to go and really measure it for themselves on their application. But, as you said, everybody may have a need doing either high volumes or low latencies. But there is some opportunity here to give up on some of that to ease the whole development and ops life cycle. So it may end up that you have a slightly larger cluster, but it means that you've got a far simpler process of getting from development into production over having a pure virtualized or a pure bare metal solution. So it's a trade-off, but what the theme we are seeing is that people are willing to make the trade-off because of the ease that Docker provides through the whole life cycle and the benefits you get overall, rather than just the resource utilization on just one axis.
Yeah, I mean, that makes perfect sense. I mean, it's what I would do in the situation given the scenario that you've described, because what I always used to, when I built systems, I was always looking for the point where it might break and try and architect for the point where it might break and make sure that works before you write it all. But, you know, in the situation with something like this, knowing how fast the bits are that you've threaded together, the approach of actually using Docker in the first instance, and if you actually hit a resource problem, which with this kind of overhead, 5 to 10%, I wouldn't be worried about that, then you can re-engineer afterwards, because what you actually got, there's an awful lot of other things that go wrong apart from performance in the development of systems, so I wouldn't particularly worry.
Absolutely.
Okay.
Yeah, and all I was going to say was that, you know, in order to make this the real advantage of these sort of environments for our customers is that you've got the inbuilt self-healing and self-discovery. So if you knit that together with the ease of deployment, now it's really easy for anybody to create big scalable clusters, whether that's in a dev or test environment, but equally important as in production. And so I think it's the combination of those attributes that make it really exciting for those teams.
Yeah, I mean that came across in the demo, and the level of sophistication which kind of comes built in, and that you can extend using Docker. I think that was fairly obvious to me. Because we're short of time, I'm going to invite Des in and the audience at the same time. Did you have any specific question, Des?
Actually, the one that's been really burning the back of my mind is I'm keen to get an insight very briefly on the moment, the epiphany to sort of shift from old school database development architectures to making the leap, and in many ways some might say leap of faith that the industry was going to go that direction towards going into the containerization, specifically Docker. I mean, you know, we've heard stories about people like Google who containerize everything, no matter whether it's Gmail or a Google search, everything's containerized. But can you share a little bit of insight into the decision process you went through to get to the point of deciding to go down this route? Because it was a brave one, I'm sure, at the time, but obviously now it's put you in a good stead.
Yeah, I mean, the premise of Aerospike goes back to about 2009, where we had some of our founders. Their background is in distributed systems. They were working at Yahoo on mobile platforms. And the realization that relational databases just weren't very good at key value lookups on primary keys. And again, look, there's an order of magnitude, these are order of magnitude slower than they should be. And the other realization was what was happening in storage with Flash. And the realization that over the edge of the horizon that their cost would come down, the capacity would increase, the latencies would improve, and so on and so forth. So Aerospike was kind of founded on the principle of utilizing and design for Flash from day one, but also the need in order to deal with the loads of the Yahoos of this world, the ability to scale out horizontally. And the realization was that at some point everybody's going to have these kind of scale of problems, whether they're an e-retailer or travel companies or so on and so forth. Containerizations for us was a simple step once you get there, which is, deploying this on bare metal and making sure that all your dependencies and everything else is correct is an operational headache. And, you know, things like Chef and Puppet help the automation, but it still doesn't give you the sense of comfort of, you know, you've baked this image and this is exactly what's being deployed and being run. And we know from our own experience of debugging production systems is a really big and ugly thing. So removing all of those dependencies or limiting to the smallest number is a huge win. So it's a combination of having a distributed system that you want the ease of deployment with really kind of makes those two technologies sing together.
It's an interesting, I'm seeing a lot of companies still struggling to deal with some of the traditional legacy scale and architecture issues, and they're all excited and keen to get involved in sort of what's new and groovy and shiny, but they tend to end up confused about, and quite rightly so, you know, the whole process of how do you get started in DevOps, how do you start thinking about automation, and then how do you finally even get remotely close to being able to do the sorts of things we've seen you do. And I don't know if anyone realized it when they were watching you, but you're obviously running Docker natively on your Mac under OS X or Unix, right?
Yep, absolutely. I mean, I think the DevOps journey is an interesting one. And, you know, I think the people I've seen who've been successful on that journey pick something simple that's kind of self-contained to understand what it means for their organization and their processes and the things that they care about. And then they kind of build from that confidence on larger scale applications. And I think that's true. It's a paradigm for adopting any new technology that works well. Trying a new technology on the biggest, nastiest application in your portfolio is fraught with peril and danger, and some people do that. But more successfully is to gain the experience of the differences of working in this type of environment. How do you get logs? How do you debug these containers? You kind of want to get familiar on that before you go all in. So that's kind of the pattern I see in terms of adoption of people down this path.
And I guess the key point of mentioning you running it natively on your Mac more than anything was that a number of large organizations are still developing. You know, they're still in sort of that typical .NET Windows, you know, pre-compiled binaries, SCCM sort of deployed model where they're just pushing out fat binaries, everything's built into it, they've got a whole Windows operating system around it. Not everyone's like yourself and the likes of, say, Jesse Frizzell, who run everything natively, and Jesse Frizzell's a fairly famous a contributor and maintainer in the Docker community. She runs everything on her desktop in a container, everything from Skype to her browser, you name it. And I sort of followed that path, and it's great when it works. But when it doesn't work, it's an interesting challenge to resolve. But you're running natively on your machine. The key point of that is that if once you get your app built and it's working in a Dockerized build model, then it can run on your Mac, it can run on various derivatives of Linux, it can run natively in Windows now if you're talking about either laptop to server. But more importantly, it can burst out of the cloud comfortably. So you've got traditional public clouds like, say, Microsoft Azure or Amazon Web Services, or more often the OpenStack fraternity such as Rackspace and Software and those crew. Once it works on your laptop, as long as you're careful about the design, it can scale out to ad infinitum, right? And I guess this is where you've really got a lead now in the market, because you've already got that natively. I guess the challenge now is how do you get people to come on the journey with you?
Yeah, absolutely. I mean, I think you've hit the nail on the head, which is the promise is build, ship, run, right? So I've built this application. I've run it natively on my Mac. My friend Jim across the table from me can now run that same image on his Windows laptop. We can go push it out to our favorite cloud or our own internal cloud, and it's still the same thing. And so I think you've got the key aspect of what this really enables, which is you can now focus on what your application is about rather than the complex management of getting your bits into all of those various forms in order to go through your test and pre-prod and your production. And because your containers or your images for your containers are now versioned, it means that Reverting is simply just a question of going back to a previous version of that image. And so the whole kind of, the management is simplified, but it also allows companies to start breaking down their big amorphous applications and running parts of these services in a container themselves, so that they can slowly demarcate areas of responsibility and draw those lines so that they can, go down that kind of microservices journey at the same time.
It's interesting that someone like Google apparently run everything in a container because, in the day when data centers were sort of considered something you could ship in a shipping container, they went from an experiment in a warehouse with shipping containers and data centers built in them or computer rooms built in them, to now that everything's running in a container at that level. There's a couple of points I'll also add. I think you're well positioned from what I've seen for essentially what they're calling the fourth industrial revolution now, and that is that with the Internet of Things becoming a thing on a day-to-day basis now, it's in the media, but we're actually seeing it come out in gadget and device sale. We've certainly seen Internet of Things happen with mobile phones. I think a lot of people forget that the Internet of Things sort of started with mobile phones when the iPhone came out. And that is that the scale and speed at which things have to be, stood up and instantiated has had to change. You couldn't wait for 2 or 3 months to procure and order a piece of hardware and build the operating system, and then we got to the point where we could do it in days with automated install of OSs and jump starts and kickstarts, and we got down to minutes, and then we got down to seconds. Now we're sort of down to the time it takes for an instruction to load into a CPU to instantiate just the bare minimum piece of business logic and code, and get the services running around it, like the network connections and memory attached and storage attached, which means that we can now scale proper Internet of Things. I don't think Internet of Things really was going to work if we had to do it the old school way. Now having the likes of a database capability in that container level is going to completely be a game changer, particularly when we realize that we can now run apps in a completely different way out to existing platforms like mobile phones. So I think Internet of Things is really only possible when technology like yours is at people's fingertips.
Yeah, I mean, it's that case of more and rapidly changing data. I mean, I think this is something that Aerospike particularly specializes in, which is the ability to read, write data concurrently. And with those kind of Internet of Things style of application, or, the Internet of moving things, when you start talking about geospatial data changing constantly, you need a database tier that can deal with the parallelism that the hardware provides, but also be able to concurrently do reads and writes. And this is kind of, some of those use cases where our customers are literally have a competitive advantage by an order of magnitude because of they're using this underlying technology.
So I'm going to wrap up because I know we're past the hour for a couple of minutes, and I don't like us to run too long. So just a couple of really quick ones, I guess. The first part is, what are the recommended steps to get people started? So if you're not already in the space and it's new and brave and exciting and you want to sort of dip your toe and get started, where should people start? And secondly, what kind of community currently exists around Aerospike, and not specifically Docker, although that happens anyway, but just around Aerospike. So, the first part, how do people get started? Where do they start? Where do they go? Where do they get the more information? And then what sort of communities around that they can participate in? Are they meetups? Are there other sort of partners and integrators and so forth they might be able to reach out to?
Absolutely. So up on our website, in our documentation, there's a bunch of guides for how to go and set up and orchestrate an application with Aerospike as a backend database. This demo is available up on GitHub, and you can go find that too. In terms of the ecosystem, Aerospike is an open source company, and so we work very closely with Docker. So there is almost certainly a Docker meetup near you where you can actually meet people with similar kind of minds. And in Aerospike specifically, of course, there's meetups, but we also have our online forums. We've got one specifically for people who are just starting with their first application, as well as Docker and containers. So there's a lot of online resources that you can get from aerospike.com. But, I'm easy to get hold of, which is, if people want to reach out directly, I'm more than happy to do that. So Alvin at aerospike.com, how easy is that?
Easy. So I'm going to leave folk with the recommendation they jump on your GitHub repository and start having a play. And also just do a quick search for a quick start for Aerospike. I think one in particular that I played with from Subfusion, there's a Node.js quick start that literally took me 3 minutes to get something up and running and play with inside Docker with a pre-build how-to. So with that, I'm going to hand back to Eric. It was a fantastic run-through. Thank you very much for the live demo. That was fantastic to see running live. It's a real litmus test to see that work. Eric, back to you.
Hey, folks, that was fantastic. Real-time application development, real-time proofing by Des Blanchfield himself. That was good stuff. Alvin, you're a brave man. Folks, we do archive all these webcasts. You can come back later and check them out whenever you have time. That should be up very shortly. And with that, we're going to bid you farewell, folks. Thanks again. We got 3 webcasts next week, so please tell your friends. Take care, folks. Bye-bye.